Hello, everybody. My name is Tyler Smith, and I am a resident at Ziva's Machine Learning and Artificial Intelligence residency program. And I have completed my third project with them, having to deal with natural language processing. Um, yeah, and I look forward to going over my notebook and the final product here in this video. So let's get after it. A little bit of background on the problem. A talent and sourcing management company wanted a robust ranking algorithm uh, to rank rank candidates via some sort of job title description. So, like an engineering manager or a full stack software engineer or aspiring human resources person, whatever that phrase may be. It could be really anything. Um, so yeah, that was a very interesting task, especially with ranking algorithms, especially like RankNet, trying to implement that and to see how um, good these models can be at classifying pertinent candidates given the job title description. In the exploratory data analysis notebook, we're going to go through that. There's a lot in this project, so I'm going to try to just kind of get through it as quickly as I can and just kind of just hit the main parts of the project. So a little bit about the data set. Um, there are 104 unique candidates with their job title, where they're from, and their location, how many connections they have, and then there's also a fit column, which won't be that column won't be used. There's another column that I'm going to use in the models notebook, so we don't need to worry about the fit column. But yeah, as we can see down here, it's not that crazy. Um, uh, Not that big of a data set, which that's kind of one problem that this problem had because there was multiple job title descriptions, such as this top one. I'll show you a little later, but this top job title right here, there's I think seven or eight, maybe nine of the same job titles in this data set, but they're all unique. So that's one problem that we face because if we had a larger data set, if it was more than 104 unique instances, maybe we could drop that title. Um, but but I digress. So the unique job titles. So like I was saying, this 2019 C.T. Bauer College of Business magna cum laude aspiring human resources professional. We can see that is uh, close to being represented 8 different times. And like I said, they're all unique, or each candidate is unique, even though their job title is the same. And we have a handful of other duplicates, such as like aspiring human resources professional and HR senior specialist and all that. But for the most part, most of those 52 most of those 52 unique job titles are unique, such as student here, and always set them up for success. I got kind of got a chuckle out of some of these job titles. Unique job locations. This was interesting. Looked like most of them were hailing from Canada, or Houston, Texas is represented. That was another thing that I found in this data set was maybe to make these a little bit more uniform, like strip out the area and the greater and uh, that kind of thing. But I didn't really feel like that was too big of an issue. There's It doesn't really appear to have many overlap except for this Houston, Texas area and Houston, Texas location. But yeah, we can just see the unique locations in the country that these people are from. These unique connections in the data set. So it'd be I'm guessing it'd be um, some sort of social media site where they can see how many uh, different connections these people have to other people, and we see that there's over 500 plus connections, or close to 50. So it's almost half of the data set has 500 plus connections, and that will be used as a kind of a decent, or not decent, but just another kind of proxy later on when we go to pre-rank the data set in the models notebook. The next part of the problem is to vectorize each job title. And what I mean by that is to put it into some sort of numerical representation that a machine can learn from. So the techniques we're going to use in the first four um, are just looking at each word individually. And the last one, that BERT that you see, that is going to be taking the whole sentence of the job title and vectorizing that into some sort of representation. So we're looking at the TF-IDF vectorization. And I'm not going to go through all of this, but essentially these first four are trying to, like I said, they're trying to map each word separately, give it its own vector representation, um, that we can use to then discern the similarity between each other, or each word, and then also on the whole, each job title to each job title. But these full sentence embeddings, which are going to be used for the next part of the problem, um, are represented here. So this generic sentence, this generic model to represent sentences, you can see here in this heat map. So on the diagonal, we're just comparing each sentence to each other, so 100% correlated. But let's say this 7% correlated right here. We're looking at this native English teacher at Epic English program in Korea as compared to this C.T. Bauer College of Business graduate magna cum laude, yada, yada, yada. And it's looking at that it's 7% correlated to it, which that stands to reason because it doesn't really look to be uh, too similar to the other title. But then we have this 98%. So this is interesting. Aspiring human resources specialist, and then we have aspiring human resources professional. So just one word out of the four on each were the same. So it's doing a pretty good job of getting the similarity of each of these job titles. Let's look at let's just look at another one before we move on. Let's take a look at this negative 73. So this is almost, I mean, it's 75% negatively correlated. So we got student at Humber College and aspiring human resources generalist, and then we have people development coordinator at Ryan. So that's pretty interesting that it's found these similarities and these dissimilarities to each other. And I did the same thing for Bert. We can see at the diagonal, they're comparing each job title to each other. And then again, this second to top left, is that's still at that 7%. This one's still at that 98%, and this one's at a negative 73 as opposed to a 75. So it's given roughly about the same correlations. The only thing that's different with BERT is that it's using, I believe it's using twice the length of features, or twice the length of numbers to represent these sentences, um, which could hurt, could hinder, but I didn't really see I didn't really see um a big discrepancy when I used both of these embeddings to implement the ranking algorithm. And so just this last heat map, this fast text is just another text to text, or it's vectorizing each word as opposed to the sentence. And you can see that the information conveyed is not quite as it doesn't quite have the variance that we saw with those other um, sentence embeddings. Um, it just looks, I mean, we still have, this now this one's saying it's 100% correlated. This one's saying it's instead of 7%, now it's at negative 15%. Um, but we're just seeing a lot of just kind of right in that range between negative 30 and like negative 30 and 20. And then it's like, we have 195, 95 here. So I didn't really want to use these embeddings going forward because I just thought there was a lot more information being conveyed um, in these BERT similarities and these generic modeling similarities than there were with the fast text embeddings. So this next part of the problem is going to be implementing the ranking algorithms or the different ranking algorithms that we'll look at. The last part of that EDA notebook, I saved the embeddings and now I'm just loading them back in. I put them in the data frame. I didn't really need to do that, but I just saw that, hey, you can do that if you want. Where that really kind of comes into play, those representations of the sentences, is here. I just put it into, I essentially just compared every job title to every other job title to see um, kind of in a more, I guess, just in a more visual way on how they're being compared to each other. So like we see this native English teacher Epic English program Korea. And I should note one thing. I have stripped the job titles of their stop words. And what I mean by stop words are all of the superfluous English words that are highly used but don't really convey that much information. So such as articles as the, and, with, or I guess with and without are prepositions. Um, but just like those words that appear a lot, that have a lot of frequency in the human language, but don't really convey that much information when these models look at them. So that's what we're looking at here. We're looking at these job titles that have been stripped of all those unnecessary words. So that's kind of why it looks kind of funny if you're reading these. But so like we have people development coordinator Ryan. So this is 65% correlated to CT Bauer College of Business graduate, magna cum laude, yada yada yada. So that's what all of this is really is trying to represent. And so as an extra feature, I wanted to average the cosine similarity scores um, for all of the job titles. So that's what we're doing down here when we see that this job title has a overall it's 72% correlated to all of them, and this one's 72, and this one's 72, and down the line. So yeah, I just put that as an extra feature to um, for the data set for training and testing purposes. All right, so this block right here, I just want to briefly comment on. This would be one of the initial functions that would be called when pre-ranking the candidates before the actual ranking process. And so what this is doing here is I'm looking for candidates that have human resources. And note again, we're using aspiring human resources as the phrase in question, the whole project. And so what I'm looking for is those candidates who have 2/3 of the title in their job title. And then what I'm doing on this next line is I'm going to say, okay, of those people who have human resources in their job title, now I'm going to look for the aspiring human resources. Now I'm looking for the full title. And so then what I'm doing is then I'm replacing And this relevancy column, this is the one that replaced that fit column. Now I don't have that fit column in there. I just wanted to use the relevancy because, well, I just thought it was a better term to use, I guess. Um, so what I'm doing is I'm replacing the binary values that this is giving me, and I'm just replacing it with a with a one and a two. So we have 0, 1, and 2 now in this column. So 0 is meaning it's very relevant, is meaning it has um it has aspiring human resources in the title. It's a 1 if it contains human resources, and it's a 2 if it has none of those. So one of the issues that was brought up prior to this whole project was how can we how can we filter out the candidates which in the first place should not be in the list? So that's kind of one um, kind of an easy way, I guess, to vet out the candidates who really aren't close to the job title in question. Um, so we can see here like the length of the human resources data set was 61. So we had 61 people of the 104 that had human resources in the title. And then the length of the non-human resources data set was 43. So the 61 and the 43, 104 people. And then of those 61, I believe in the prior notebook, it was 35 people who had aspiring human resources. So we're having 35 people who are clearly relevant. What is that under? I think it's 28 or 27 people who are kind of relevant, and then 43 people who just are not who are not being considered for aspiring human resources um, position because they don't have that in the job title. So that's kind of this pre-ranking mechanism that we're going to be using for later on during the actual ranking implementation. Oh yeah, like I said, here we go. We have 26 candidates that have aspiring human resources in the job title. We have 35 that have the human resources in their job title, and then we have 43 that do not have any of that in their job title. And so now we're looking at the full data frame now with all those embeddings. So with those embeddings that we were using in the prior notebook with those BERT embeddings, it has 760, 700 and let's see, 700 would be these just I think 766 since it's a zero index, and then we have just extra features such as connection and cosine similarity. They're just extra features for the training and testing purposes. And then this would also be ranked by the relevancy, the cosine score, and the connection. So we're ranking this now. These are all the embeddings of all of our candidates with their cosine score for the whole and for their connection. How many connections do they have? And so we're first ranking them by the relevancy, which I took out because you don't want that during training and testing purposes. We're going to rank that, so it should be 0, 1, 2. So the top one should be first, one should be in the middle, and then two's at the bottom. And then we're going to rank it on cosine, and then we're going to rank it on connection. So that's how I did that. And that should be another function. If we were doing this in a development environment, that should be after this block right here. So just FYI. And the rest of this is all of this is just for the RankNet implementation, and I'm not going to go through this because um, this is just a lot of it's just a lot. So if you want to look at that, you can. Um, this is the training part of it, and then as well as the final ranking um, to then use um, on that ranked data set. So the next part is lambda rank, and again, I'm not going to go through this. I've linked a good link that I thought was helpful in doing this. So if you want to read more on what lambda rank is, I'm implementing it here with a training and test set from that data set that I explained above, and just just hyperparameter tuned both the LGBM and the X gradient boost ranking algorithms to see which one was going to produce the best scores using an NDCG score and an accuracy score. And so using that X gradient boost ranker, I found that this performed pretty well without needing any hyperparameters tuned. I did, but it didn't affect the accuracy score by anything. So that was kind of interesting. But as we can see, it's doing a pretty good job of, all these job titles have aspiring human resources in them. And if they don't, this one does at the end. We just can't see it. Um, here's the student that crept in. But I mean, for the most part, it does a pretty good job. And so this final function is recursively calling itself to then pre-rank the pre-ranked um, data set that we had previously looked at. So then we can see, and so how that really works is we take that pre-ranked data set, seeing, if they have aspiring human resources or if they have just a human resources or if they have none of that in there. We're taking that pre-ranked data set, we're feeding it into the X gradient boosted ranker, and we're going to extract the top ranked, so essentially be this top ranked index. We're going to extract that top ranked index. We're going to append it to a list, and then we're going to do the re-ranking again on that same list, but without that top candidate. And so we're going to do that n times. So you can just put in however many times you want to do to do the ranking for you. And so now we see that we get a different list than if you would go up above to look at the X gradient boost ranker initially. It gives you a different result of candidates because it has done the pre-ranking n times. In this case, it's done it 10 times. So that's really going to be the final product here, because as we'll see with prompt engineering using large language models, the prompt engineering gets very time intensive, very resource intensive. You need a lot of hardware, you need a lot of memory. This one gives you a pretty decent final result, barring again that we have candidates such as these three, this 14, 1, and 44 that have the same job titles. But like I said at the onset, we don't have that big of a we don't have that big of a data set, so we can't really take out we can't take out half of the data set to train on. It's just it'd be too small. So given this task, this is my or given the task, this is my final suggestion that we use an X gradient boosted ranker to do this task, just because it performs well given what we're wanting, um, uh, without all of the memory and all the hardware or the resource issues. But do let's look at the prompt engineering section, and we're just gonna prompt it by saying, you're a ranking algorithm that ranks a list of candidates based on how similar each item is to a given phrase and returns the top n items that the user requests. And then we'll query it and say, in this list of items, and we're going to provide it a candidates list up here. I'm just going to give it the candidates list and their unique IDs. And I want you to give me the top 15 items that are related to the phrase aspiring human resources. Now, like I said, with the time intensive, I mean, this took 85 minutes to train. But once we got the result, this is pretty cool. So I mean, look, we have it's saying here the top 15 items related to aspiring human resources, and we have aspiring human resources professional. We have an HR senior specialist at Ryan. We can go down the list, and then it gives us this sentence down at the bottom. It says these listed items are directly focused on individuals who are in the process of gaining qualifications or experience in the field of human resources or are preparing for careers in this particular sector. So it even sort of, I guess you could say, to anthropomorphize it, it rationalized or it gave some sort of reason why it ranked these candidates the way they did. Because if you look up above to the X gradient boosted ranking, they are different. So I had to do it in Google Colab because if you run the right environment, such as like a TPU or a GPU, you can get this to work. Um, but like I said, it takes a long time. Um, so I queried it just like the prompting I just showed that it says, can you give me a list of the top 15 candidates that have aspiring human resources in their title, as well as the reason that you chose each candidate? And now prior to that, I did, oh yeah, yep. So yeah, so I did train it on I did let it look at the documents. So in the data, um, actually it's not on here, it's on yeah, it'd be on the Google on my Google Drive. But anyway, it was just the the data set that was given at the onset of the problem. I let that train on that data, and then query it about the candidates in that list. And so, although it didn't give me 15, and this might be because I did not set a token max length um, that I would have to look into, but it only gave me the f top five. But if we look at that original data set, you'll notice that the top five were just the first five from the data set, so it didn't really rank them. Um, and I actually just noticed that after I made all these other secondary and tertiary queries. So that's why I then queried it again that said, why did you choose, that should be choose. Why did you choose why did you choose the first candidate when there were other candidates that had that same job title? Because I knew that this job title came in up 7 or 8 different times in that data set. So it's, why did you choose the first one? And mind you, again, I didn't realize that he just or um that the model just took 1, 2, 3, 4, 5 straight from the original original data frame. But then its response said the selection was based on the specific requirements or preferences outlined in the query. The first candidate was chosen because they had a relevant educational background and were located in the desired area. And then that prompted me to say, well, what do you mean by desired area? And then it said the desired area refers to the generational or the geographical location where an individual is seeking employment opportunities. And you can read the rest. And then, of course, my environment um, shut down. I wasn't able to see a response from this next query. But yeah, it's very interesting working with these large language models, and they do have a very good use case. I just feel like in this problem, it's not necessary to use all that extra memory and use those extra resources. And this is just fine. It'll automate the process and give us good desired results. So yeah, thanks for bearing with me for the how long I've talked here, and hopefully you've um got a little bit of knowledge out of it. And yeah, if anybody wants to connect with me on LinkedIn, it's just Tyler Smith. And yeah, if anybody has any questions or comments or want to give me some feedback or anything, I am all ears. So thank you, and we'll talk to you later.